Okay, so continuing with weld defects and non-destructive testing, let us try to look into what are the kind of defects one may expect in case of a welded joint, a fission welded joint, because these defects we will be talking about, not necessarily they will be there in case of solid state welding or friction stir welding. These are the these defects you may find in joints done by electric arc welding, electroslag welding, electrogas welding, or in other words fusion welding. So, as I was saying, the flaws depending on type, location and size. Well, as far as the location is concerned, as you can see, there is a, say, a welding has been done. Now, a flaw can be at the surface, a flaw can be somewhere here on the upper surface of the joint, can be at the lower surface of the joint, can be at the bottom, can be at the middle, different location in different orientation, right. Depending on where it is taking place also is important, right, because depending on the location its detection becomes different. That is number one. Number two, depending on location it may qualify for a flaw which can be ignored. Like for example, a small crack inside and similarly small crack outside, the outside is not, the inside one maybe can be ignored, say the size. Now, next comes the size. Size is beyond the critical limit, I mean less than the critical limit. So, you can ignore this, but this you cannot ignore. Why? Because of the simple reason, the critical length of a crack is half when it is a surface crack. Say L is the critical length. Suppose, what is that critical length? Suppose, well, assume some critical length, like when you talk about fatigue failure, right, whether the crack will propagate or not depends on whether the crack length is less than or beyond a certain critical length. If it is beyond more than the certain critical length at the operating stress level, then the crack will propagate faster, right. So, if we talk about that critical length, the critical length becomes half if the crack is at the surface. Okay. So, that is how the size of the crack, I mean the location of the crack also depends, or location of the flaw. In generalized term, we are talking about flaw. It can be crack, it can be something else, it can be a foreign particle got lodged inside the molten metal. That is also a discontinuity. A crack is essentially a discontinuity. So, we will essentially look for discontinuities, whatever is there inside a welded joint, right. Wherever it has caused discontinuities, those are flaw. Now, that flaw will become a defect depending on the type of the flaw, depending on its location, depending on its size, right. So, these are to be ascertained once you find. So, those will be ascertained through a non-destructive testing technique, which is called NDT. Through NDT, we will ascertain what is the type of the flaw, where is the location and what is the size. Then that will tell us whether that flaw is a defect or not. If it is a defect, remedial action has to be taken, right. So, that is how. So, let us see now what are the so called defects one may observe in case of fusion welding. We will talk about the ones which are more I mean so called mostly observed and which are more which has a predominant effect on the performance of the structure. So, first and foremost is a so called lack of deposition. we will first try to sort of make a list of the defects which are probable, and then we will see how and why, how they are forming, why they are forming, and what is to be done with them. So, lack of deposition. Similarly, lack of penetration. Over deposition. Just reverse of lack of deposition, over deposition. Something called undercut. Right? Spatter. We will come to that. I am trying to sort of, you see, again, if you go by this location, some will be surface defects, some will be internal defects. So, depending on the type of surface defect or internal defect, again you will have different methods, mechanism to find them out. So, we are trying to group them as the surface defects, then we will go for the internal defects. So, as of now I can see these are the ones I can recall which are the kind of surface defects. Within that also you have surface crack, surface cracks, right. Then you have internal cracks. Once we have talked about surface crack, means there can be internal cracks, right. There is something called slag inclusion. Slag inclusion, the name suggests what it is, right. Then you have what you call porosity. Then you have blowholes also one can talk about blowholes. Then something called lamellar tear. So, these are the defects internal. They are the internal defects, right. So, that's how we see there are surface defects, internal defects. Now, all these they may take place because of again improper weld parameters, right, because of improper weld procedure, because some may depend on an improper procedure, means the welding parameter is a part of welding procedure, because welding procedure will tell you about the entire process which is to be followed. that includes what should be the welding current, that also includes how much restraint is to be applied to the plates, right. So, depending all those factors working together may lead to one of these defects, right. If these defects, I mean here we are talking about the defects, and we are assuming that the size of the porosity, the size of the undercut is such that they are to be removed. That means their location is in the cracks, the surface crack or the internal crack is in such a location that they are to be removed, right. The size is such that they qualify for defect. Anyway, so lack of deposition, as you can see, the very name, that means it leads to a good welded joint. Suppose a butt welding is being done, right, it should lead to a weld profile like this, right. Instead, if it leads to a weld profile say like this, then this is lack of deposition, right. It should be a convex, the bit profile has to be convex, that means there should be a crown on the metal on the over the fusion zone where the metal has been deposited, a crown, a top, a reinforcement should be there. This is what is referred to as top reinforcement. So, this is what is lack of deposition. Lack of deposition. This may happen because of improper weld parameter, like higher welding speed, less melting rate of the electrode has led to improper deposition. Proper full deposition hasn't taken place. So, that is lack of deposition. Then lack of penetration. Lack of penetration is, that is, say again, suppose a butt weld is being done, right, and the fusion zone looks like this. That means deposited metal did not penetrate through the thickness, and there is a lack of penetration at the root. Root deposition hasn't taken place. There is lack of penetration. So, this is obviously is not acceptable. Like lack of deposition is not acceptable because here the cross sectional area becoming less, so your strength of the joint might be less. Similarly, here it is more serious, lack of penetration, because this part will act as a gross discontinuity in the structure, will behave like a crack as if. So, there will be a much greater stress concentration. Lack of penetration is more severe defect than lack of deposition, right. So, this is what is lack of penetration. Then, well, over deposition. Over deposition is just the reverse of it. Over deposition is this. Well, what is the problem with over deposition? Over deposition means, you see, that will, yeah, firstly it is unnecessary, too much of heat has gone into the structure. Extra metal has been deposited means extra heat has gone there. So, that already has a adverse effect by increasing the heat affected zone. The heat affected zone will be more. which is a indirect defect, which is not immediately visible, whose effect will not be immediately visible, but in the long run that might affect. I have a wider heat affected zone. Wider heat affected zone means a wider place of inferior mechanical property, right. Heat affected zone is not only is inferior in mechanical property compared to the parent metal, it is also a zone where corrosion rate is higher. Why? Because there you may have residual stress, plus the corrosion may get initiated there. Why? Because there is the microstructure is different to the adjacent microstructure. So, the cathode anode formation will take place, a galvanic cell, localized galvanic cell will take place. So, that is one aspect, that because welding procedure also should look into such that it will lead to not only a joint defect free, but also a joint leading to minimum width of heat affected zone, minimum residual stress, minimum distortion, right. So, over deposition, one aspect is this. Other aspect is, of course, as you said, that local stress concentration, because here at this corner there is a sudden change in the cross section, a sufficient change in the cross section. So, a stress concentration is expected. So, that is also not a I mean that is not desirable. So, over deposition can also be taken as a defect. What is to be done? Lack of deposition, if it defect, what is to be done? Well, simple, you will have to deposit additional layer, you will have to re-weld it, simple, to get the proper deposition. Here what is to be done? You have to grind it, you have to use a grinder, cut it off, right. So, that is what is over deposition. Then undercut, undercut we have already talked about before. It is a case, what happens is, when welding is done, now if the welding speed is too high, then at the edges of the weld bed, the weld reinforcement forms like this, and at the edges, right, a small narrow channel like a thing forms. Why? Because essentially the metal gets melted, right. If the speed is fast, metal gets melted, and the metal, because of the high speed, the metal gets solidified faster before it could flow back and fill up the entire place. So, a kind of a crater is formed, a longitudinal crater all along the length of the weld. It is speed dependent, means if speed is high, it generally leads to undercut. That is what is referred to as undercut, though nothing is happening at the below the weld bed, but it is at the side of the weld bed. This is my weld bed at the side, right. Small such channels will form as if. So, that is what is referred to as undercut. So, if this undercut is there, now the trouble is, this is happening where you have the heat affected zone. The undercut is near the zone, is above the heat affected zone, and as it is, heat affected zone is mechanically weak. So, having an undercut is a serious flaw. So, it has to be taken care of. That means, the weld bits to be it has to be re-welded and this undercut to be removed. And what happens, since it's related to speed, so whenever there is a case of undercut, it continues for a certain length before the welder observes that this is happening. Then only you stop the weld process, check the parameters and redo it. So, that is what is undercut. Then spatter. Spatter is a thing you see, it's not a directly itself is not a defect. Say this is my weld line, right? This is my weld line. That means along this the welding has been done. Say a butt joint has been done, a butt welding. That means two flat plates have been welded, and you see in some location there are a lot of such small droplets of metal droplets are there. This is what is referred to as spatter. Spatter in itself is not a flaw or a defect, but it indicates that there might be a flaw here. Wherever the spatter has taken place, there might be a flaw there inside. Because why spattering has taken place? What is spatter? What caused spatter? That means expulsion of metal has taken place for some reason or other, right? So if that has taken place, there can be a possibility of gas has got entrapped in the process. That means there was a turbulence in the weld pool. Because of that, molten metal has got expelled from the weld pool. In the process, there could have been an entrapment of gas. So spatter means there can be a possibility of porosity inside. A porosity may have formed, right? So spatter, though itself is not a defect, but it points to a defect. That is what it is. And also at the same time, wherever spatter has taken place, these droplets are to be removed. They are to be removed by grinding, because if they are not removed, then later when you do painting, corrosion will start there, because paint film will get damaged because of the spatter, and corrosion will start there. So that is what is spatter. And then you have the so called surface crack. Say a welding has been done, there is a weld bed, and you see a crack in the surface. A crack can be a vertical crack. This crack can be a through and through crack. It can be on the surface, localized crack, right? That means a line crack or a star-like crack, all kinds of cracks that can be on the surface, right? So these are essentially surface cracks. Surface cracks means the cracks which are visible on the surface. They may be few micron deep, they may be few millimeter deep, they may be several millimeters deep, they may be through and through crack, all kinds. That means just on the surface thin layer has got cracked, or it can be deep. It can be as deep as the entire thickness. Through and through there is a crack. That can also happen. Generally these cracks, these surface cracks are generally referred to as hot cracks. Hot cracks means they take place during the welding phase itself, during the welding process itself. That means you are welding a joint, and as you look back, at the back it has already cracked. That means still the weld is hot. By hot I do not mean that they are still in a liquid state, because in liquid state there is no crack. Means it has solidified, but it is still hot. It has not fully cooled down, but it has already cracked. So that is also referred to as solidification cracking. Solidification cracking, that means as if during the process of solidification it has cracked, right? So generally surface cracks are due to solidification cracking. They are generally hot cracks. Well, what happens? Because of stresses, because of unfavorable thermal stresses taking place, the structure is unfavorably restrained. So, the kind of tensile stress taking place in the weld metal and the weld metal composition taken together, it cannot sustain that stress and crack develops. So, what could be remedy? Well, remedy is once the crack has developed, if you have detected it, that has to be scooped out, cut out and re-weld. That is the remedy. Otherwise, procedural remedy would be, you have to look into the weld parameters, you have to look into the filler metal composition, you have to look into the structural restraints, say butt welding, a fillet welding you are doing. In fact, just the other day we had been doing I was telling you probably in the previous class, just a simple case of fillet welding we had been doing, right. So, with a submerged arc, the fillet was like this, both sides fillet, right, and a crack was observed right in the center line, through and through crack, from the surface till inside, through and through crack took place. In the second case, when we did some, means this was a case, a small test sample, hardly 300 millimeter long, like this, right. When it is welded, it cracked all through, all along the length. The next, before welding, we did some tacking at some small intervals, small tack welds, and then welded, there was no crack. That means the stress redistribution taking place, or simple because of some tack welds have been done, and then when you are welding it, the stresses developing are totally different, or the extent of tensile loading coming on the fillet, it is not cracking it. So, that is why the surface crack, it will depend on, well, it will primarily depend on the welding procedure. It will depend on the restraint on the structure, what kind of stress level is taking place. So, if a defect is observed, well, it has to be removed and re-welded, but thereby you are not removing the cause of the defect. So, to remove the cause of the defect means you have to look into the welding procedure, such that newer fresh welding you do, crack or defect should not occur. So, these are the defects we talked about. They are the surface defect: lack of deposition, lack of penetration, over deposition, undercut, spatter and surface cracks. Those surface cracks can go inside, right. So, they are the kind of surface defects, and then you have the internal defects. Internal defects, we started with internal cracks. In this case, what happens? In this case, when the welding has been done, from outside, both side, top, bottom, everywhere, it looks absolutely perfect. That means nothing is visible, but there can be a crack inside, not visible. Crack can be vertically downwards, can be oblique, can be horizontal, anything, right, or it can be even in several directions, like this, internal cracks. These internal cracks are generally referred to as cold crack. Well, once again, the internal crack, like surface crack, the cracking has taken place at the surface and propagated inside. Internal crack can get initiated internally and may get propagated outside. So, it may or may not become visible outside, generally not visible, remains trapped within, inside. Internal cracks, they are generally cold crack, and cold crack is due to a phenomena called hydrogen embrittlement, right, because of hydrogen embrittlement. Means this hydrogen is making the rendering the material brittle, is as if it is rendering the material brittle, and thereby the material is cracking. That means it is losing its ductility, natural ductility, becoming brittle, and under the thermal stresses or under the formation of the residual stresses after the welding, everything is over, it is getting cracked. So, that is what is generally the internal cracks are like that. What basically happens is, little bit if you look into this, once again you see the go back to the so called microstructure. If we look into the microstructure, we see somewhat like this. That means, in between the grains there are spaces which are some voids are there. These are the voids in between the grains. Like, so what happens when you are doing welding, if there is a hydrogen present in the environment, where from? From the moisture. Moisture in the flux, moisture in the plate, moisture in the electrode wire, or environmental moisture. If there is too much moisture is there, that from the moisture that hydrogen gets, that H2O gets dissociated, right, and in hydrogen in atomic form they get lodged in these voids, microstructural voids, right. In between the grains the voids are there, the hydrogen in the atomic form it gets lodged there, they occupy those spaces, and as the welding is over, the entire material gets cooled down. At that condition, those atoms they combine and forms the molecules, right. Once that is formed, they exert a tremendous force in all direction. Why? Because it seems the molecule, the volume is more than individual atoms. That means, two atoms combining forming a molecule, the volume occupied by two atoms is less than one molecule, right. So, thereby once the atomic hydrogen gets converted to molecular hydrogen, it exerts a tremendous pressure, because the volume it was occupying is becoming short. So, in that pressure it cracks, right, in that pressure it cracks. So, thereby as if the hydrogen has made the material brittle and the metal has cracked, right. So, that is what is referred to as hydrogen embrittlement. So, in that form such cracks may form inside and may get initiated and stopped within. That means, it does not further propagate. Later, under action of external forces, etc., other kinds of loading, that may act as a so called may act as a further crack initiator. Means, from there the crack may grow, crack growth may take place and eventually lead to a catastrophic failure of the entire structure. So, that is what are the internal cracks, right. So, they are generally because of this hydrogen embrittlement, and that is why they are referred to as cold crack. Means, it is something like this. Also, they are referred to as delayed cracking. Delayed cracking means, the welding has been done today, immediately after say few hours, if you check the welding, you may find there is no crack, but after 2 days you might find a crack. That also happens. So, that is the internal crack. Then you have slag inclusion. Means, when you do a multi-run welding, suppose with a manual metal arc welding with a multi-run, means one run you have given, then whatever slag was there you have removed it, you have given a second run, a third run, and so on. Every run you are giving, you are removing the slag. If you do not remove it meticulously, a small speck of slag may remain inside. Suppose a slag has remained here and you have done welding on top of it. So, what will happen? The slag does not get remelted, it remains, neither it floats up, it remains. So, that is a slag inclusion, the slag has got included. Slag inclusion is, if I look it in a enlarged form, the slag can, that slag particle can have any arbitrary shape, and in all probability that arbitrary shape will have very many sharp peaks. Why? Because the slag is a brittle material, it is the hardened, that burnt flux, right, it is a brittle material. So, a small speck remaining means it will have all kinds of sharp edges. So, this, the slag inside will behave as a, these edges will behave like a crack tips, and if there is a crack tip means chances of stress concentration. The moment there is a stress concentration means there can be the potential crack initiator, the location for crack initiation. So, this is slag inclusion, again a internal defect. Porosity. Porosity is again, if your welding speed is not adequate, rather on the higher side, then what may happen, the gases what has been formed because of, depending on the process, suppose you are using shielded metal arc welding, the flux is burning, giving out gas which is shielding the molten metal, or you are using gas metal arc welding, the gas is injected on the weld pool surface for shielding. So, the gas bubbles, they get entrapped before they can float out, they get entrapped inside. Before they can float out, the metal solidifies and gets entrapped, and a cluster of such small, that is the difference between blowhole and porosity. Blowhole is rather a bigger diameter void, a void of bigger diameter, that is a blowhole, a gross entrapment of a gas bubble, right. Whereas porosity is fine droplets kind of a thing, much finer sizes of cluster of small blowholes, as if very small blowholes, a cluster of them is referred to as porosity. So, porosity can be a cause due to higher welding speed, it can be due to presence of impurities in the welding site. Suppose some grease or oil is there, that gets burned, that also generates gases, fumes which gets entrapped. So, porosity, naturally porosity has to be removed, that is a gross defect, and it is a internal defect at the same time, because it forms within the fusion zone. Blowhole is same thing, it is a formation of a porosity is a cluster of small bubbles, blowhole is one big bubble. For some reason, some gas bubble may got entrapped. Generally, blowhole is not observed. Blowhole is observed in casting operations, when you do molding and casting of big parts. Suppose you are doing the casting of the stern frame of the ship, right. If it is not properly done, the mold etc. not properly prepared, gases may form which cannot escape and forms as a, remains as a blowhole. Here we have generally porosity. Then lamellar tear, it is a typical failure in case of fillet joints. In case of T joints, suppose a structure is like this, right. The welding is done in this fashion, these are the fillets. Fillet welding, like immense amount of fillet welding is done in the ship structure, all the stiffened panels essentially is fillet welding. So, when you do fillet welding, what is happening? The material here, material around the weld zone, I mean a shrinkage force works there, it shrinks, isn't it? This is shrinking in this direction, this part is shrinking in this direction. right? A shrinkage force works, and depending on a situation, sometimes a defect of this type is observed. A crack forms in the base plate over which that T member, or that means this is fillet welded on the base plate, a crack forms. This is what is called lamellar tear, lamellar tearing, right? This is because of the thermal stresses. Here it has this lamellar tear, has nothing to do in the weld zone. It's generally just beyond the weld zone. It can be in the heat affected zone, just below the fusion zone, right? So that is what is lamellar tear. Once again, lamellar tear is also a internal defect. So these are the typical weld defects, as we can see. Now the job is to should have a mechanism through which you can detect all these defects. So we have seen that there are surface defects as well as internal defects. That means we will have to have mechanism by which we can see what is there in the surface as well as what is there inside. So based on that, in fact, to tell you, as far as welding, so-called, as far as non-destructive testing techniques are concerned, there are several techniques are there, several methods are available, but obviously many of them are not suitable for shipbuilding applications or the kind of structures we do. There, many of them are not suitable. So we will discuss about only those which are relevant to shipbuilding. What could be the first and foremost and most important and most sort of most effective, efficient means of NDT, non-destructive testing? What? Visual inspection. Nothing but a visual inspection means a very trained eye, inspection through a very much a skilled and trained eye, visual inspection. Why? Because you can very well appreciate the extent of welding which goes in a ship structure or in an offshore structure or any structure of that type. Extensive amount of welding goes in, isn't it? I mean, if you really put together the in terms of meters, it will be few hundreds of kilometers, probably the total weld length that will go in a vessel of probably 200-meter long, right? I mean, few hundreds of kilometers total weld length will be there probably. So obviously now it becomes probably physically impossible to have a very extensive check on the entire weld length. So what is done is visual inspection is the most important. That is done for the entire welded or the entire weld length is subjected to visual inspection. What does it mean? It means that a proper weld inspector or a person trained in welding defects and these things, he physically checks. He physically checks the welding from outside through visual inspection. Thereby, you can already detect as many as these 6 defects which are there on the surface. So already so many could be detected. There can be something like some of the surface crack may not become visible in the naked eye. There are some other methods then one can apply, but at least others, lack of deposition, lack of penetration, undercut, over deposition, spatter, all this can be detected. So visual inspection is a technique which is in fact the most effective means of testing or assuring whether the welding has been done defect free or not. But obviously its limitation is you can only through this check the external or surface defects. Next is what is called dye penetrant testing. this method is also used in shipbuilding applications. What is that dye penetrant? Means essentially this is used like, as far as visual inspection is concerned, lack of deposition can be very easily detected, lack of penetration, over deposition, undercut, spatter. All these 5 can be very easily detected, but surface crack may at times evade your naked eye. Means they might be so fine that you may fail to notice it, and obviously you will not go about with a magnifying glass. That is not done. Anyway, so surface crack you may evade unless until it is a very wide and visible crack, right. So, to help that visual inspection, one can take help of dye penetrant testing. So, through using a kind of a dye, it enhances your capability of visual inspection. What is done is, over the weld surface, a fluorescent dye is sprayed over the weld surface. By capillary action, the dye propagates through the crack, right. And then what is done is, you just clean the surface, wipe out the surface. So, whatever dye has got penetrated in the crack, that crack may be surface crack. Means I am not talking about through and through crack. It can be just surface crack. It can be to a certain depth, starting from the surface. So, dye will penetrate by capillary action, and if you rub the surface, I mean wipe it out, what will happen? And that surface is illuminated with a fluorescent, with a ultraviolet torch. With the ultraviolet torch, that fluorescent dye will glow in that, right. So, the cracks will become easily visible. That is the logic. That is how you can detect those cracks. Of course, this does not tell you how deep the crack is. Obviously, it does not tell you, but it gives you that, well, there is a crack on the surface. There is another aspect of dye penetrant testing. If you are testing a flat plate, this side you have put a dye and you go on the other side and illuminate that with a ultraviolet light. If some part glows, that means there is a through and through crack, because through capillary action it will suck to the other side. It will go, the dye will go to the other side. So, if something is bleeding on the other side, which becomes visible in that fluorescent, because of its fluorescence under ultraviolet light. So, you can make out that there is a crack through and through. So, that is what is the dye penetrant testing. This is a very simple method of testing, inexpensive but effective. What the primary drawback is, limitation is that it cannot say whether, it can only say either it is a surface crack or it is a through and through crack. If it is halfway between how much, it cannot say, because if you have to repair the crack, then you should know how much it has gone in, right. Also, another drawback is, it does not have any, same drawback for visual inspection, no record. You cannot, automatic records are not generated. You will have to later prepare a record that there was a crack, that was the defect, etc., right. That is also a limitation. Next method is called magnetic particle method. There is another method called magnetic particle. In this magnetic particle, what is done is, you have a, suppose the welding has been done along this line, right. Over this you spray iron filings, iron powder rather, over the entire, over the welded surface. Say iron powder is put, and then you move a magnet, a horseshoe magnet suppose, in this direction. You just move the magnet along the welded zone. So, what will happen? You know, the magnetic lines of force will act through this. So, this will, all these magnetic filings will align themselves as per the magnetic lines of force. Now, if there is a discontinuity in between, about that discontinuity again a north and south pole will form. As you know, since here I am having a north pole and there is a south pole, right. Say there is a discontinuity here. So, in this discontinuity closer to this side will become south pole and the other side will become north pole, isn't it? Just reverse magnetic fields will form. So, this side it will form a south pole and the other side of the crack will form a north pole. And again there the magnetic lines of force will be disrupted. So, the those powders, iron powders will align themselves along that crack, right, and the crack will be visible. Through the arrangement of those magnetic particles of the iron powder which has been spread over it, they will align themselves along the crack and the crack will be visible. So, that becomes a very simple method of testing. But what are the limitations? Well, first and foremost limitation is it has to be done in a horizontal case. That means the plates are remaining in the horizontal form. In a vertical, you cannot do magnetic testing. Die penetrant in vertical also you can do. Overhead, not possible. So, in a horizontal. And second limitation is the material, the welded material has to be magnetic. That means for aluminum welding I cannot use. Third is it has a limitation in the penetrating power of the magnetic field, penetrating power of the magnetic field. Generally it penetrates up to 6 millimeter. That means any crack beyond 6 millimeter, suppose a discontinuity beyond 6 millimeter below, say you have done checking a plate of 20 millimeter thick, crack is there on the bottom half below 10 millimeter, that will not be visible. It generally penetrates up to 6 millimeter. So, that is the limitation of magnetic particle testing. Well, next is the radiographic testing. Radiographic testing is nothing but the conventional X-ray as we do, similar to that. It will be more powerful X-ray basically, right. So, the X-ray you all are aware of. In the same method, you will have to put a photographic material below and over you expose it with X-ray. So, whatever defects inside will get a image there, and again a trained eye has to read that film. Something like your lung X-ray is done, a doctor will know whether things are all right or not. Same way, a welding doctor will know by checking the X-rays whether there is any, the spots whatever will come, whether it relates to a crack or relates to a slag inclusion or relates to a porosity, right. Similarly, you have ultrasonic testing. Ultrasonic testing is again, well, with radiographic testing the biggest advantage is you can literally see through the entire weld fusion zone through the material, all defects you can see, but at the same time it has limitations that supposingly your defect falls in line with the crack. Suppose assume a theoretical crack like this, a vertical crack, and your X-rays are coming vertically down, so it will give a spot in the film. You will not realize that there is such a long crack is there. You will find it's a small, possibly some defect, small spot. Though that is hypothetically it is possible, but such a coincidence can be rare. Other disadvantage of radiographic is hazardous. That is number one, very much hazardous, and second, it's a bulky equipment, so not very nook and corner you cannot test. Whereas ultrasonic testing, it uses the principle of sound. A sound wave, whenever you put a sound wave, whenever it meets a interface, it gets reflected. That is how, in that principle, even these probes can be used as a thickness gauge. I put it, these probes are small probes which can be held in the just by the fingers. So, it is more portable, you can take it out anywhere within the nook and corner, or a complicated structural geometry is there, it can be taken there. So, these ultrasound probes are used in a zigzag fashion. This is the weld line. The ultrasound probe is moved in such a fashion on both the sides of the weld zone. This is the welding line, this is the movement of the, why it is done that way? Because these probes have a capability of transmitting ultrasound in a oblique fashion, right, in a oblique direction. So, if the weld zone is this, you go on moving this, it scans the entire depth. You make this movement of the probe, so it scans the entire depth. Again, on the other side, it will scan the entire depth. So, thereby it goes on scanning the entire depth. So, any discontinuity it is meeting within the weld zone in the form of a crack or a slag inclusion or porosity, it will be reflected in the monitor, because otherwise the monitor signal will be something uniform. Wherever there is some discontinuity, there will be some spike. Again the same thing, what this spike means, what extent of crack, etc. Again it needs a very trained interpretation, right. Something similar to that of, you see the ECG plots, again something similar, you will have to be trained in that, but the logic is, point is, through this you can very easily see what is there inside, and the same thing can also be recorded. That is another biggest advantage of radiographic and ultrasonic testing, that you can produce a record of the tests. That is very, very important from legal point of view, because you know what happens, all these assumes a immense importance if an accident takes place. In the service life, some accidents take place, then you start digging out, start post-mortem and all that. So, there this thing becomes very important, that well, these weldings were tested and these are my reports. But all these visual, dye-penetrating magnetic particle, no report. Report is man-made, means after you have seen, after done, you can write it down. But this is in the process of testing, reports are generated. The photographic films or the prints of those from the ultrasound probes, right. So, these are, that is how we see these are the basic 5 techniques which are used extensively. What is done is, the vulnerable parts, say the bilge plate, that welding of the bilge plate and the side plate, the shear strake and the side shell plate. So, such vulnerable joints, they are 100% radiographic tested. These are all specified by classification society rules, that what type of testing is a must. Visual inspection is a must for entire weld length. Very vulnerable places, radiographic or ultrasonic testing is a must, right. So, that is how we see that these are the NDTs which are primarily used in shipbuilding. There are many more, but in shipbuilding these are the most relevant and these are the ones which are used.